All right. Thank you, Jessica. So I think this mic is only connected for the video. So if you can't hear me, let me know and I'll speak up. OK, so today's tutorial, like Jessica said, will be about how to build. Oh, you can't hear me. OK. I'll try to speak up or speak louder. So today's tutorial will be about how to build your own self-driving car. I don't have code examples that you can follow along with necessarily. This is a project that took me 6 months, and so it's hard to condense it into a really small amount of time. But I hope to teach you some lessons that I learned along the way, so that if you're interested in building your own self-driving car, I can save you those pain points. So yeah, here's a picture of my car. I actually have it with me today. If you want to come up after the presentation to see it, but it's a little yellow Ferrari. It's about 12 inches long. Okay, so a little bit about me. Oh, it's got cut off, actually. All right, let me change the aspect ratio on my computer. Yeah. Okay. All right, this is not ideal. Is that better? Yeah, is there any way I can shift the shift to the yeah? No, it's full screen on my end, so. Okay. Well, yeah. Yeah, there's definitely a missing chunk there. Yes, go. All right, so this first slide is not super important, so I'll just keep going on this one. So yes, my name is Ryan Zotti. I'm a software data engineer at Capital One. Yeah, thanks. So I've been at Capital One for 4 years now. I joined right out of college. I do a lot of kind of odd side of the desk projects, and this is one of them. But I like data science. I like machine learning. I have two publications in machine learning. One was to predict if various antidepressants will help relieve depression from people suffering from depression, and that was published in the Lancet earlier this year. And then I had another project working with a professor from my school to predict real-time stock price movements from tweets and basically like natural language processing. So that's pretty cool, or that's what I like to do. Okay, so why did I do this project? So I've been doing machine learning for a while now, and I don't have a lot of that I can showcase really. So I wanted something really tangible, and I think the self-driving car is like a great example of it, meets those criteria perfectly. So I had never actually done any kind of machine vision projects before. Most of my data science machine learning work has been with gradient boosting or decision trees or linear models, stuff like that. And I never actually used machine or deep learning, or in particular like neural networks these days are very, very popular. And so I wanted to kind of see how I could play around with that. Okay, another thing I want to note is I'm not actually the first person to build their own self-driving car or their own self-driving remote control car. There are plenty of other examples of people doing this if you just do a quick Google search. In particular, the examples that I really liked are this one to the left, actually, by Zhang Wang, this red SUV kind of thing here. He has some really good work. He has like stop sign detection, which I have today. He has stoplight detection, so he can detect whether a stoplight is red or green. And then he can, I think he used some machine learning to predict the distance that a stop sign or stoplight is from the car, so it knows when to stop. And I thought that was really great. This one to the right can do, I think it was made by some high school students in Amsterdam. I think, and it can basically do parallel parking, and it can change lanes and avoid obstacles. And then this top one, I think, is kind of this top. Oh, is it still? Is there any way we can shift the projector a little bit? You'll let them know. Okay, perfect. Yeah, so there's lots of different ways you can like design your car. The way I've done it isn't necessarily the only way or the best way. I've seen people use like mount a smartphone on top of their car. Yeah, I kind of liked Zheng Wein's approach, the bottom left, but like Betty, my fiance here, said it was too ugly to do it that way, so I had to try to cram everything into my little car this way, which is a bit of a challenge. You're really constrained for space, and I kind of recommend it. I'll talk about this in future slides, or in later slides, but one of the lessons I learned is you want to get a bigger car because the Raspberry Pi and the battery and all those things really take up a lot of space. So if you want to keep everything in the car, get a bigger car. And that's, I think, kind of why a lot of other people before me chose to use a smartphone, because a lot of the intelligence, you don't actually need the Pi necessarily in the car. You can have your machine learning algorithm run on a server somewhere, and then stream. All the video handling capabilities will happen on the phone, and you just stream all that data over the network to your server, and then back the commands go back to the car. Okay, so some materials. Let's see. Okay, so I spent a lot of money on this project. All of these pieces individually are pretty cheap, but they add up, and they definitely add up if you break them and have to buy them multiple times. So that was the case for me. The toy car itself was pretty cheap. It was like $30. I got it at Target. The Raspberry Pi is, depending on where you buy it, is like $29, $32. I got my first Pi. I got the Raspberry Pi 2 from like a starter kit on Amazon, and that was like $50, but it included like a charger. It included a protective case, which I didn't use, and like in hindsight, I should have, because my Pi broke. So definitely, I definitely recommend you invest in a case. It's a pretty cheap investment, and it'll save your Pi. I had to get a webcam. So the Raspberry Pi camera is really great. Can I get a raise of hands? How many people have tried or have played around with the Raspberry Pi before? Okay, like a third of the room. Yeah, so so for those that haven't, the Raspberry Pi camera is really easy to integrate with the Raspberry Pi itself. You really don't need to install any extra software. Everything just kind of comes with the Raspbian Pi operating system. But the camera is actually in some cases more expensive than the Pi itself, and it's pretty effective if you don't short it. But I'd shorted both of my cameras, so I burnt through a lot of money pretty quickly there. So that's why I have this Logitech webcam. It has a terrible resolution. You wouldn't want to use it as an actual webcam, but for a self-driving car, it has like sufficient resolution, and it's like $10, or you can even get it for like $5 if you buy it on eBay. The Raspberry Pi, most kits will come with a micro SD card. Those are generally like the one that comes with. If you buy the kit on Amazon, they're usually like 8 gigs or 10 gigs, which is probably enough for most small projects. But I have a very data-intensive project. I have a lot of libraries that take up a lot of space, and so I very quickly ran out of space, basically. And so I just bought a 64 gig micro SD card, and that's what I've been using. And I still have quite a bit of space after that. So that was about $20. You can get that at Micro Center. So a pro tip. So I kind of hate shopping, and I bought all these things on Amazon. But in hindsight, what I learned is it takes a few days to get for shipping, and sometimes these, I would get these pieces from, like, especially like the webcam, I would get these from overseas, and it would take like 2 or 3 weeks to get them. And if you're kind of tinkering, you want, and you're doing this every other weekend, you just want it like right now. So I really recommend Micro Center. It's kind of like the best place for a dork to buy stuff. I love Micro Center now. I drove Betty, my fiance, crazy because I would go there all the time. But yeah, you can buy all these things at Micro Center, and will save you a lot of time. So anyways, I got the external battery at Micro Center, I think. The battery is really important, especially if you have a small car, because it just takes up a lot of space, but also it's really heavy. So I had to kind of experiment with it, a couple of different batteries, and actually the battery that I liked most was one I got for free, actually, and worked best. So you don't necessarily want to go for the charge capacity, but more how much does it weigh and how well does it fit inside of your car. You need copious amounts of wire. I broke a lot of wire when I was doing my soldering, and you want wires of different lengths, so just get lots of it. You'll need soldering equipment, and then if you want to do like obstacle detection or kind of like arbitrary obstacle detection, you want ultrasound modules, and those are pretty cheap. You can get like 10 of those for like, I don't know, I think $5 if you order them from overseas. So this is what the this is what the car looks like on the inside. It's kind of a hot mess. So we've got, you'll see in the, I guess you can't see the mouse, but we've got the battery on top there. I've got my breadboard, which you probably don't need a breadboard. I probably could have, done some more soldering to get rid of that, but it didn't take up too much space. But underneath that, you'll see the Raspberry Pi in its case. And actually, so does I actually have my broken Pi, which I can pass around if you guys just want to kind of like look at it. Whoops. Are you guys changing the video? Yeah. Perfect. Let me go to a slide where the text got cut off. There we go. So I think like there's this whole like dark portion. All right, so I'm going to pass around while we're waiting. If you guys are ever curious what a Pi looks like. But this is a broken one, so feel free to just do whatever you want with it. But I'm going to pass it around in case you want to look at it and see what it looks like. Too many times. Okay. It's already at the pretty low resolution. It's like 1024, 760. I don't have that resolution option.
You're at 8.6. Yeah, that's the
I can just kind of move it.
I think it's within your DA there.
I think it's within the DA. All right. I'll try to swap that out after the next session.
Okay. Because if you runs directly into the board display, okay.
Yeah, that's all right. Because the signal that's sending us back there, you can see it all.
It's perfect.
Yeah, that's why I didn't think it was the DA.
Okay.
But I'll definitely try to change it out after. I know sometimes with the scaling resolutions we have this issue. But...
Yeah, okay, that's fine.
All right, sorry about that.
No problem. All right, so let's see. Okay, so this is the inside of the car. All right, so you'll see that I've got the battery. It's really small. The Raspberry Pi, which is in a case. So I thought, like, they say, the Raspberry Pis come in these like protective cases that prevent electricity from kind of messing with it. But I thought, I'm not around anything kind of dangerous. It's fine if I just kind of throw it in my car. But I very quickly learned that will break really fast. So definitely get a case. Let's see. So I've got the battery, the Raspberry Pi. You'll see in the very front that's the ultrasound. If you have a bigger car, so my ultrasound is a bit limited in the sense that it can only see what's directly in front of it. It can go pretty far. It can go a few meters. But if you want to do parallel parking, or if you wanted to make a car that could race other people's cars, and you didn't want to kind of like T-bone somebody or get T-boned, and you wanted to have like obstacle detection on all sides, you'd want to have a lot more ultrasound sensors than I have. But I just didn't have space for more, basically, because there's a lot of wiring that's involved, even though the sensor itself is kind of small and on the outside. Okay, let's see. All right, so here's my training track. I used paper. So my car is, the motor is really weak, and it's actually so weak that I can't run on the carpet. It barely moves with paper on a carpet. So I think a lot of other examples people will have the paper as kind of the boundaries of the road, and as long as you stay within the boundaries of the road, that's good enough for them. But I actually had to make the paper my road. This looks kind of this is not very professional. I'm sure I could have had a better looking track, but basically I liked using the paper because I could make different kinds of tracks. I could generate a lot of training data. So that's what I used. And it's ugly, but it gets the job done. So, yeah, question?
Yeah, so the car that you're talking about,
Mm-hmm.
How do you control the movement of that thing?
Good question.
Is it like just a regular car which when you push it just goes straight, or can it swivel?
Yeah, it can swivel. Well, it can't. It's not. So it can definitely like turn left and right. The wheels aren't like well, they're not on an axle either, but yeah, are you asking like if it can turn? I mean, or if it can, what do you mean by swivel, I guess?
Does it have a motor on it that you can control?
Yeah. So actually, I'm going to take a really quick tangent, and I'll show you some of my code if you're interested. So I have all this on GitHub, by the way. If you just go to GitHub, Ryan Zotti, self-driving car. Let's see. Okay, so the Raspberry Pi code is really easy to use. I've got a lot of extra code here, but the important stuff is, where's my motor class? Here we go. No, this is not it. So basically, whenever you kind of interact with the Raspberry Pi, you have to import basic Raspberry Pi packages, or just this one package, actually, or one library. But basically, there's like different pins on the Raspberry Pi, and depending on how you do your wiring, you can kind of like turn various pins on or off, and then via soldering and connecting some wires to the actual motor of the car, you can tell, my particular car has a motor for steering, for going left and right, and then it has a motor in the back, a stronger motor, for just going straight. So if I turn on the motors for going straight and I turn on the motors for going left, the car will go left.
The car itself is an analog input,
Yeah.
and the Raspberry Pi has no analog, right?
Actually, so I have to be honest here. So my electrical knowledge is horrible. So I got it to work somehow. I'm not sure if it's analog or not, but I think it's. I thought it was analog, but if you know more than I do, then maybe it's not analog.
For what?
The car itself, and it's an on and off. So,
Okay. So you just
stroke
pulse
the thing,
it.
the wheel snaps over to the left, and that's the end of that, and then it makes the turn next.
Yeah.
So it doesn't have a step level.
It may, but I suspect that the way you wired it up, you get the full 5 volts, the wheel swings.
So you're just controlling the angle by the duration of the pulse.
Yeah. So actually, I do know the answer to that part. So I know, but thanks for that addition. I use pulse width modulation. So I had no idea what pulse width modulation was before. So maybe that answers your question. Yeah. So basically, I actually have. Let's see.
And then the other question is, why don't we use the battery from the car to power the
Good point. I ran out of time. I did that. I found that out on accident one time. So I had this really bad habit of like destroying my Pis on accident or shorting them, and I'd accidentally connected it to my 6 AA batteries, and it was like, my battery is off, or my auxiliary battery is off. Why is my Pi still on? And then I found out because it was connected to the AA batteries, and like I was really scared at that point because I had just destroyed a Pi, and I was like, I'm sure if I throw some resistors in here, I can get it to work, but like I've got like minutes before this thing blows, so I'm just gonna unplug it. Yeah, exactly. So, yeah. So basically, you use pulse width modulation. The more frequent your pulses are, the stronger the current, and the more left or right the motor will go, or forwards or backwards. But basically, you assign you assign these pins basically.
It says GPIO PWM.
Yes.
There we go.
Yes. Yeah. So I'm completely self-taught here. I've got a lot of glaring knowledge gaps. So like I do know, like I've made this work somehow, but there might be like basic things that I can't explain, but I'll do my best. So let's see, where do I go from here? Okay. Yeah. So you define your pins, and then somewhere here I have my pulse. So change duty cycle. So this is how it's like from a scale of 0 to 100. What percent or how frequent do you want your pulses to be? So basically, in a lot of these cases, I'll set my pulse to be like my car is the motor is so weak that I just set it to 100% pretty much for when I'm going forward or left or right. But that's how the code looks. Okay. So this is my training track. All right. So what I'll demo today. I have various sessions that I've taken from the car camera itself of it driving in my very contained environment in my apartment. I'm a little scared to do it here, so I have it recorded ahead of time. But I'll also demo the stop sign recognition using Haar Cascades, which is a really fancy machine learning technique. It's used for facial recognition in photos, and kind of, I think the post office even uses it for identifying handwritten digits on paper. and then I'll show you how to train a neural network on a GPU on AWS. This last one, I tried logging into my AWS account yesterday, and it said your new limit for GPUs is 0. So that was a little frustrating. So I'll see if I can get that working again this morning. But if not, I'll probably demo Tensor Board, which is TensorFlow's machine learning dashboard, basically, which is pretty cool too. All right, so I'll show you some of the footage I have of the car driving itself. I'm going to go to my Python code. Hopefully you guys can see this. So basically, the dimensions of I'm basically reading it, a video file. Here we go. I'm going to replay this because it's really short. My track is not that long. Okay, here we go. So you can see it's going over the paper. It knows to turn right, looks ahead, it knows to turn left a little bit, then it gets to the end and it stops. So it's very fast. So when I was training my car, I had to do this myself many times to generate data for the car to learn from. And I spent countless hours generating this data.
Playing around with the car.
Yeah, exactly. Yeah, yes, just toiling away,
Toilet.
Yeah. Yeah. And Betty had to put up with me the whole time. I would go to my dork cave and work on this car, and yeah. Yes. Yes. Question.
The important question is, did you read or see The Martian before or after all of your short-out experience?
Yeah, I have seen The Martian. It is a great movie, but after, yeah, I could have learned something. Yep, absolutely. All right, so that's the car in motion. Let's see, how am I doing on time? Okay. All right, so this is my really basic tech stack. Oh, you can't see it. All right, okay, here we go. This is probably not ideal. I'll go back and forth between full screen and not. I've shifted everything over a little bit. So I've got a Raspberry Pi at a high level, of course. I've got OpenCV and TensorFlow, and I'll talk about each of these in detail much more later. But all you really need to know is that it's 100% Python. If you know Python, if you know a little bit of Linux, and if you know machine learning, TensorFlow is probably the most challenging piece here. If you're just starting, if you haven't done any machine learning, TensorFlow is very challenging. If you have some experience, it's probably the easiest of the neural network libraries out there, I think. But anyways, all of this is in Python, which is great. Oops. Okay. All right, so this is Raspberry Pi. My fiance, who helped me make this PowerPoint pretty, insisted I put a literal Raspberry Pi in the top left there. But the actual Raspberry Pi that I'm talking about is this green thing I'm passing around, and you see right here. It's $30 approximately. It has 1 gigabyte of memory. It has a 1.2 gigahertz CPU processor. It has a micro SD storage slot, so I put 64 gigabyte drive in mine. It runs Raspbian Pi Linux, which is I'm not sure which distro it's closest to, but yeah, it's Linux. It has built-in Wi-Fi, or at least the Raspberry Pi 3, that the third generation has built-in Wi-Fi, and it's essentially a mini computer. So let me point out some of the features of it. If you aren't already familiar with it. So we've got 4 USB ports. We've got an HDMI. I'm not sure if this, I guess this port that's in the top or bottom left is for Ethernet. We've got an HDMI port. There's the thing on the top right, I guess, is where you would plug in the camera. We've got all the GPIO pins. And then there's the charger, which is kind of in the top center. And yeah, so that's the Raspberry Pi. I actually bought both a Pi and an Arduino at first. I wasn't sure which would work best. The Arduino's on the bottom there. I can't say a lot about the Arduino because I fell in love with the Raspberry Pi and I never really looked back after that. So, but I guess kind of the reason I thought about using the Pi first was that it has a lot more. It can do a lot more than the Arduino. And one of my original plans was to run the neural network on the Pi. And when you're processing video images and doing anything with TensorFlow or OpenCV, you need you need a decent amount of memory. And I could be wrong, but I don't think the Arduino had that. So that's why I went with the yeah. Question.
Well, I had two. One was with the Pi,
So I haven't played around with like just saying like the read and write speeds to the SD card. Yeah, I haven't really. I just kind of bought. I'll pass around. Okay. Yeah, I got them one that was cheap basically. I don't do a lot of reading and writing to disk. I do have a lot of data that I write to disk, but everything, all of the processing that happens is in memory. So yeah, I don't think the read and write speed has made a big difference for me, but there might be other use cases for it.
And then the other thing was you had it looked like a resolution display up earlier, and you were running it 800 by 600. It looked like there was another option. So a lot of projectors don't like 800 to 600. Try that. It might.
Okay. Oh, you mean like for the presentation mode?
Yeah.
Okay. Let's see. Oh, is this better? This is. I should have done that. Whoops. Oh, it is. All right. Well, there we go. That's all I had to do. All right. My bad. Perfect. Thank you. Okay. So, yeah, part of the reason why I went with the Pi in the beginning was it has a lot more, compute power than the Arduino does. In hindsight, it didn't really matter because the Pi it's great for if you're not doing a lot of compute, but anything with machine learning involves a lot of compute, and I think more than the Pi can really handle. The Pi can do it, but I need, my camera gets like 20 frames per second, and the rate at which the neural network, when it's running on the Pi, can create predictions or react to the frames is like 300 to 400 milliseconds, which is not good enough. So basically, the car can't react very quickly when it's driving if everything is just purely running on the Pi. And so I had some trade-offs. I originally wanted to have all of the machine learning done on the Pi so they could react faster, because I was kind of wanted to save. I've worked on a lot of prediction or I've deployed a lot of machine learning models in my work at Capital One, and latency is something that's really important, and we try to minimize network hops. So I kind of wanted to avoid having a lot of sending data back and forth over the network to reduce latency, but it turns out that the latency hit you get from running on the Pi is substantially greater than the latency hit of just transferring these predictions and frames over the network. So I ultimately went with running the neural network on my laptop or on a server. And so I would basically get video frames from the Pi, send those over the network into my machine learning algorithm, which would ingest them, and then output the control or the command back to the Pi, which would then interpret it and move the motors accordingly. So I can actually, like to train the models or like run it, like deploy it. So it can actually run on the Pi. I mean, it works. But to get it within like the amount of latency I would need, I don't know, like 20. Yeah. So it can run on the Pi, and I have. It's just like I'll get I'll have like 20 frames per second coming my way, but I'll only be able to really do anything with like 3. Like I can only act on like 3 of those frames. So basically, if I have a really narrow road, it just kind of overcorrects, or just kind of not overcorrects, it undercorrects, I guess, and it'll just kind of go off to the side. So I want something that can react really, really fast. Yeah, so that's why the latency mattered so much. So basically, ultimately, the network latency was less of a problem than the Pi latency. So I did all the heavy lifting on the elsewhere, basically. So in hindsight, the Arduino might have been fine, or maybe not. Maybe it's okay. Yeah. Okay, so I have zero background with, I'm not an electrical engineer. I've never really tinkered with electronics. This is my first project doing this. So the Raspberry Pi seemed kind of intimidating to me. So I was really excited when I could just get an LED light to work. It was, yeah. So the importance of the LED light is if you can get the light the brightness to change, it means you can get pulse width modulation working, which means that you can get your motor speeds to change. So it was just an LED light. I never actually used the LED light in my car, but it meant that it was the first step of the hello world, basically, of the Raspberry Pi. Yeah, so it was a very big first step. And then basically, I really need to document this because if I lose some wires, I'm going to have to Google search all over again. But basically, just gradually add more and more functionality on. The first step was basically, can I get the front motors to move? Great, I got that working. Can I get the left and right motors working? Yes, got that. Can I get the rangefinder ultrasound working? Yes, got that. and I gradually pack on more and more and more wires, and then it's just this giant mess, tangled mess here. So yeah, all right. Pro tip: don't inhale lead. This was my first time soldering, and I didn't realize that the solder material that you actually use to fuse onto the wires is actually 35 to 40% lead. And actually, after doing some Googling after the fact, I found out that like the worst way to get lead poison, or the strongest way of like ingesting lead or whatever, is by inhaling it. And the problem is these wires are really small, and my solder equipment was terrible, so I had to get really close and like put it up next to my face, and it was just like inhaling all this smoke. And then I read, oh crap, that's not a good idea. So I probably, if my presentation sucks, it's blame it on the lead poisoning. Yeah, but in all honesty, like soldering, I've had friends that have soldered before, and they're like, oh, it's easy, no problem. But I don't know if it was my tools or my incompetence, but I found it really challenging. Yeah, don't blame the tools. Yeah.
There's a trick to it.
Yeah.
You can do a lot of solder.
Yeah, I used my entire solder, like the metal thing on these two wires basically. It was really sad. Okay, so OpenCV. So the hardware is more of my weakness, but I'm pretty good at, or I consider myself pretty good at machine learning, and this is where I can probably answer most questions that come my way. So OpenCV is it's an open source computer vision library. If you want to do anything with machine vision, anything with images or video, and you want to use Python, you will probably come across OpenCV. I'm not aware of any alternatives. So has anyone else done computer vision stuff and used something other than OpenCV with Python? No. Okay. Yeah, so probably OpenCV is kind of what you'll use most likely. OpenCV does a lot of things. If you're trying to install it on the Raspberry Pi, it's going to take a lot of space. But basically, it converts images and videos to basically matrices. There's a lot of submodules in it. You can use it for object detection. In particular, something called Haar Cascades. I might be pronouncing that word wrong. It's Haar Cascades. And I'll show you that in a little bit with the stop sign piece. It's all open source. It's got a Python API. I think it's built on C++. And yeah. So this is the Haar Cascades module I'll talk about. And actually, if you've done machine learning, or can I get a raise of hands? How many of you have done machine learning before in even a trivial way? Okay, so wow, most of you. Wow, cool. All right, how many of you have heard of gradient boosting? Okay, most of you. Okay, perfect. Yeah, so I actually didn't realize this. So gradient boosting is kind of an older kind of algorithm, and you generally almost never hear it associated with machine vision. Usually you think of neural networks with machine vision problems, but Haar Cascades actually uses gradient boosting, and it's like it's generally like a 100,000 tree model. So it's really, really big, a really big gradient boosting model. But basically it predicts, you can train this, or OpenCV has this Haar Cascades module, which will train a GBM on whatever you're trying to identify. In this case, from the OpenCV website, it's basically for facial recognition. It's very efficient. Probably one of the first questions I had when I was trying to figure out how this actually worked is, you'll see in a second that the Haar Cascades algorithm can actually detect objects of various sizes anywhere in the image. And so the first question I had when I was tinkering with this was, how does it efficiently find what you're looking for? Does it scan the entire image? And if so, isn't that really expensive? And the answer is yes, it does actually scan the entire image, but it does so in a very efficient way. So for those of you that have done gradient boosting before, you'll notice that when you're training the model, you train on the errors of each subsequent tree that you're training is basically, you're trying to predict the previous tree's errors. And so it's kind of like a series of stages. And the authors of the Haar Cascades algorithm were really smart about this. And so the vast majority, so for example, in this picture right here, there's the algorithm is trained to look for a face. Most of the image does not contain a face. There's just those two faces there. So the first part of the algorithm basically can catch 80% of the faces, and then there's maybe 50 more stages after that. If the 80% of if the first stage doesn't see a face, there is almost always not a face there. So there's no point in evaluating the subsequent stages or phases. So it's actually not that expensive to go across the entire image or scan every single pixel pretty much, or a set of pixels. There's a little bit more. They kind of handle the there's another like efficiency gain they have by doing something else, but it's a little complicated, so I'll gloss over that. But it does scan over the entire image, and it's really actually very efficient. Yeah, sure.
How does it know that the faces are the objects we're looking for, and let's say not the windows? What if I want to isolate the windows out of the picture?
Sure. Yeah. So you basically, when you're training your algorithm, just like you for any kind of other machine learning use case, you have to basically pass it a bunch of positive examples and negative examples. So if you wanted to train something that found bananas or windows in your case, you have to pass a lot of examples of windows and then a lot of examples of things that aren't windows. Yeah. And basically, if you've used like scikit-learn or H2O, or if you use R, if you've used like Caret, you'll like there are certain kind of like machine learning standards you expect to see in an interface for for doing machine learning. But in OpenCV's Haar Cascades algorithm kind of breaks a lot of those standards and is really hard to use for that reason. But it kind of like it'll resize things for you, and you don't really have to think about that. But yeah, basically the underlying concept of I pass positive and negative images is still the same. No, I did not actually. So I think others have done that. I found that using color worked reasonably well. And actually, in a little bit, I'll show, or I won't really show, but I'll demonstrate, or I'll talk about how the neural network that like guides the car along the road performed a lot better with color than with black and white. But I have seen others use black and white as well.
And the graphics card, or whatever the graphics functionality of the Raspberry Pi
Mm-hmm.
doesn't have any of the compression stuff on it.
It might. I'm not sure. I haven't really like thought about compression. Like compression, like.
Because a lot of the computations that you use to do compression
Mm-hmm.
are what you would use to do your, the first stage of your Haar transform.
Yeah, I'm not.
And you didn't think about putting on a graphics card.
So I actually did train the model on a GPU, but I didn't.
You didn't think of putting a GPU on your car.
No, that would actually be interesting. I haven't. GPUs are also really expensive. Like if you get, that can be like a couple grand. But if there's really, that's true. Yeah. So I've got a Mac, so I'm like everything's just in this pretty little box right here. So like I'm not used to playing around with graphics cards. But yeah, I guess that's a good point. Okay. So the stop sign detector. So basically, I use the Haar Cascades algorithm to detect stop signs. One question most of you might be thinking is, so why don't you just, in this demo, why don't you just show it from the car? This project is, this is still something, a feature I need to integrate into the like overall car project. This project is still in progress, but I'll show you at a high level how it works. Yes.
The featureization process that is going on here with respect to the images,
Mm-hmm.
is that happening before you send it into the neural network? Or is there any way of doing featureization within the neural network, so using OpenCV?
So to convert.
The idea here, the reason I asked this question is like if you do it before sending it into neural nets, you have control over what you do, and that way you don't know what's necessarily good and what's not. But with neural nets, it can create its own features that I'll resume using OpenCV and find the ones that work best. So I'm just trying to understand the approach here.
Yeah. Yeah, so for Haar Cascades, I didn't use neural networks, but for the neural network piece, for the driving component, I didn't really do any feature engineering. Would you, like the vast majority of data science projects, machine learning projects involve, like if you've ever gone on Kaggle or competed on Kaggle, that's like the really where you can get the most bang for your buck is not so much the model you use or the tuning parameters, it's really how you do your feature engineering. And I did no feature engineering for this project. I just took the raw matrices and just jumped it into the neural network. And the idea was, and I started with like the kind of deep convoluted neural networks, which are really popular right now and almost a buzzword in the machine vision world, because they can generate their own features. So I didn't do any feature engineering, and I only used OpenCV for the ability to convert the images and video frames into matrices.
Essentially, if I understand this properly, so you're featureizing the images using OpenCV and sending out the matrix
Yep.
into neural nets without doing any PCA or without doing anything else.
Yep, that's right. Yep. Yeah, I didn't compress anything, so maybe that's what the gentleman's question over there was about. So I don't do singular value decomposition or principal components analysis. I'm literally passing in all of the pixels to my neural net.
Just out of curiosity, how many features were you dealing with?
200,000. Yep, that was a lot. So the Haar Cascades piece here. So we've got this thing. So this library is really hard to use in OpenCV. Actually, it does what you want it to do when it's all done. But it ran on a single core, which was kind of frustrating, and it took 2.5 days. And Betty accidentally closed my laptop one time and freaked out, and that was kind of funny. But yeah, it took a long time. I recommend standing up an EC2 server on AWS maybe and just kind of letting it do its thing, because it literally took 2.5 days. But it works really well. So, and I'll show you that now. All right, so I'm gonna open up my PyCharm coder. Actually, I'll just do this in the terminal. Let's see. Okay, so again, I'll integrate this into the car in a month probably. But right now I'm just going to stream video from my webcam, and I've got a little stop sign right here. Okay. So here is the webcam, and you can see.
Get right out of town.
Oops, it has to be really flat. But yeah, it's not 100% accurate. Like I thought my face was the stop sign at one point. But it gets the basic.
When you turn it, can you rotate it slowly so that it gets less octagonal? Yeah, like that there.
So yeah, it's.
Oh, there we go. Okay.
So yeah.
Pretty cool.
Yeah. So yeah, it is pretty cool.
And this is running through the network. That is car plus. Oh no, it's all on the Mac.
Yes, this is all on the Mac.
Using the Pi.
Yep, that's right. But actually, Haar Cascades, the algorithm is pretty lightweight, and I could run this on the Pi if I wanted to.
Or if the Pi camera was being used instead of the Mac camera, it would be just that fast.
Yeah.
Okay.
Yes, the Haar Cascades algorithm is very fast. If you have other kinds of object recognition things you want to do, it doesn't have to be a stop sign. It could be a face. It could be whatever. It can be as effective as this. So it's.
It just takes some RAM. I mean, you're trading off flops for RAM.
Yeah.
Which you have a gig of. So.
Yeah. All right. And so you can detect other things too. So the Wang Zheng, the guy I was talking about earlier, he did this for stoplights. So he can detect green versus red stoplights and other obstacles. So I want to do that next, I think. All right, TensorFlow. So the most challenging machine learning Python library out there, I think. So it's Google's open source machine learning library. I think it came out in November of last year. It's used primarily for training various flavors of neural networks. I think you can also train linear models with it, but I don't believe at this time that you can use it for gradient boosting or random forests or other kinds of bread and butter algorithms. If you have some machine learning experience, I would say maybe a year of it potentially. It can be easy to use. The Hello World example of it is really easy to use. You can just, even if you're not sure what you're doing, you can just copy and paste it and it'll work out of the box, or at least it did a few months ago. It's very fast. Recently, I've heard that, or not recently, like a few months ago, 4 or 5 months ago, I heard that it is pretty scalable. You can now there were a lot of complaints actually when it first came out that it wasn't scalable, that you could only run it on a single GPU or on a single machine. But now you can, there's out-of-the-box support for multiple GPUs. You can have a cluster of GPUs. So that's pretty cool. I haven't tried that yet. I want to try that soon. It's got a Python API. It's written in C++. It's incredibly popular. So if you go by the way I gauge the health of an open source project, as I look at how many, there's a lot of different ways of doing it, but you can look at how many people have starred the repository on GitHub. So let me just show you how I would do that. So in case you don't believe me, we got, let's see, TensorFlow, GitHub. So TensorFlow has 33,000. Actually has like 200 more than it did a few days ago. Approximately 33,000 stars. I just looked at some other popular open source projects. I don't know JavaScript at all, but Node.js I've heard is a popular JavaScript framework, and it's 27,000. Apache Spark, which I do know, which is like kind of the most popular thing in the big data space, is 10,000. So TensorFlow is incredibly popular, and I recommend you learn it if you're curious about neural networks. All right, machine learning 101. So what is machine learning? I think everyone here is, or most people here are pretty familiar with it, it sounds like, from the raise of hands that I got earlier. But basically, it's pattern generally, it's kind of a similar sequence of steps that you follow when you want to apply it. You have to collect a lot of data. There are there's like a subfield of machine learning called reinforcement learning, where you can learn by example on the fly. It's called reinforcement learning, and it's you can if you wanted to make an AI that could play chess really well or some game, that would be reinforcement learning. But the vast majority of machine learning cases are supervised. You basically have a lot of labeled data. You have a labeled data set. You say, here are some inputs. Here's what I actually got or what I want to get. Find patterns in this input data that can predict this output. So you have to collect a lot of data for these supervised learning kinds of problems. So I actually had to drive the car myself a lot to generate that data. When you get the data, you generally have to do some sort of cleaning. Like I was saying, for most standard machine learning problems, like on Kaggle, for example, this is probably the most important part. Doing your feature engineering, creating clever features. Machine vision is really popular right now because, in theory, you shouldn't have to do any feature engineering. If you have the right kind of neural network tuned, it will do the feature engineering for you. You have to train lots of different types of models. This could be, gradient boosting. It could be a linear model. It could be a neural network. Even neural networks are really interesting, and there's even different flavors of neural networks and different ways of designing and architecting them. And you want to try all of them because you never know ahead of time which will work best. When you finish training all these different kinds of models or algorithms, you test it on a new set of data that the algorithm has never seen before when it was learning, and that gives you a decent sense of how it would do if you had deployed it to the wild. So once you've put all of your trained algorithms through this test, and you know which one has performed best, you'll select that one for deployment, and then you can put it on a live system like your self-driving car and see how it actually performs on a completely new track. So this is how a neural network sees. I actually got this image from Zheng Wang's blog, but it's really clever and really does a good job of illustrating how my network works. So basically, we've got this image. I think his image was a lot smaller than mine. My images are 320 by 240 pixels. And then because I'm not doing it in black and white, it's actually 3 color channels. So it's roughly comes out to be about 200 some thousand pixels per frame. It's a lot. But basically, the way this works is, so you've got this image on the left here. In his case, he's not driving on paper. He has his paper as the boundaries. But all of these pixels are being fed into the first input layer of the neural network. So you've got a lot of nodes. I'll have 203,000 or whatever it is nodes in the input layer. You can have however many. Generally, for a really simple neural network like this one, you would have only one hidden layer, and you kind of just try out various counts of inner nodes or inner neurons. He picked 32, and I actually picked 32, and 32 worked best for me. And I don't know, maybe it's not a coincidence that it worked best for him as well. But those calculate. The neural networks are kind of a black box in the sense that once the model's done training, you can inspect the node and look at all of its weights, but it's not. You can't really interpret much from it, so it's just kind of a black box. But then these 32 hidden nodes are passed to the final layer, which is used to make a prediction of some sort. So in my case, and also in Zheng Wang's case, he's predicting there are 4 class labels: turning left, turning right, and going forward. I actually didn't use reverse. I think he said he just threw in reverse just for the fun of it, but didn't use it either. So I just have 3. But I think he trained with 4 classes. So that's how the neural network works. This is I want to pause here for a second because this is a really important consideration. If you're thinking about building your own self-driving car, and if you have a car that's more powerful and bigger than mine, you might want to design these classes differently. I was reading a paper from I think it was MIT or Berkeley or one of those self-driving car hubs, research hubs, and I think they have 32 class labels. So there's different you can have a sharp turn, a normal turn, and then a really shallow turn or just going straight. And they have there's 32 different ways of defining a turn. And my car is so weak that it's really. I've tried doing different strengths of turns, but it's really just a one kind of turn thing. So I have only 3 classes, but you could have more classes than that. You might even be able to represent it as a continuous kind of thing, like a degree turn maybe. And so I don't know if what I've done is necessarily the best way of doing this. And it's I don't want to belabor this point, but this is a really important decision to make. Also because when you're training the algorithm, when you're providing the labeled data set, especially in my case because I had a really wide track, there are cases where it could have either hugged the road, going to the left maybe, or gone straight, and either would be correct. But when I was driving, I kind of arbitrarily picked, to stay in the middle or to go off to the side a little bit. And so the neural network, there might be like 2 right answers, but the labeled data set only shows 1, and so the error rate can look really high, even though it's not necessarily, it doesn't necessarily mean that the model is performing poorly. So if you had more, more classes and there was more leeway about which class was right, you might get a different error rate. So it's just a really important consideration if you're doing, if you're thinking about the machine learning behind this for your own project, you'll spend a lot of time thinking about this problem. Okay, so I'm going to talk about, the different flavors of neural networks. Convoluted neural networks, they are literally convoluted and hard to understand, but they're literally doing convolution as well. Basically, the way they work is you have your first layer, which is the layer at the top, and then subsequent layers basically learn more and more complex features. So generally, the first layer is supposed to learn edges. It might learn blobs or curves. And then if you're doing facial recognition, for example, the next layer might learn eyes or a nose. And then the last layer will actually compose all of these pieces together to make a face. Convoluted neural networks are very popular right now. They're very in the field of machine vision, and they're I would say overhyped maybe, but they're very promising, and they've represented a big step forward in terms of object detection. Let's see. So they are very effective because they share weights. So I think the neural networks have been around for many years. I think maybe even since the 70s or earlier. But they weren't very effective because you'll see in a second. How much time do I have? Okay. Because they have a lot of connections, and that can lead to overfitting. In my case, I found using TensorFlow, the API is not so hard to use, but it's the convoluted neural network itself is very hard to tune. So deep learning, people are kind of like marketing deep learning as the solution of all the world's problems, but deep learning basically just means a neural network with a lot of hidden layers. It's a really deep amount of layers, and this is one of the reasons why neural networks kind of went out of fashion maybe a decade or 2 ago, is because you have all these connections and it can lead to overfitting. And while your error rate might look really good on your training data set, it'll look horrible when you deploy it or on your test data set. But this can give you kind of a sense of the complexity of a deep learning model. You've got your input layer in the far left. You've got multiple hidden layers which are learning features on their own. And then you've got your output layer, which is predicting, in this case, maybe going left, going right, going forward, or going backwards. This is a standard neural network. This is what I used, and this is what actually pretty much everybody else that has done this on Google, made these hobbies have done as well. It's just the most simple flavor of neural networks. Is a single hidden. It has a single hidden layer, and I was very surprised. I've done a lot of research on convoluted neural networks and deep learning, and I had very high hopes for it, but it was pretty disappointing. And the simplest model actually performed the best. And when I was kind of reading about other people's projects, a lot of them were done by students, college students, and kind of figured that they were doing this for a really quick, a project that only lasted for a semester, and so they were kind of crunched for time, and maybe they didn't have a lot of machine vision experience, and so they just kind of used the easiest thing, which would be a simple neural network, and that's why they picked that. But I think in hindsight, they might have tried other things, and this is just what worked best for them, because that's what happened to me. I tried convoluted neural networks and other types of models, but ultimately this far outperformed all other model types, and I was very surprised by that. Yes? Good question. So the activation function, are you asking about the activation function?
Well, I don't know much about it, so I'm just trying to understand what does each layer provide the process?
Sure.
What is activation?
Yeah, so the activation, so let me know if I'm getting too deep into the math here, but so basically, yeah, sigmoid. So there's different kinds of, so the activation function is basically the kind of mathematical operation that you apply to your numbers, the input data. Yeah, so I use this is sigmoid. I use sigmoid. I found that sigmoid worked best. I was surprised because a lot of people say that if you have a really deep neural network, you can have when you're updating your weights, the updates will get lost in the middle, kind of, because the rate of change is very small, or basically almost zero, on the edges here. So in a lot of deep learning applications, you'll see people use things like what's called the rectified linear unit. I won't really talk about that much because I don't want to put people to sleep. But I started using ReLU units. They didn't really work very well in the convoluted neural network. They didn't work at all, I think, in the shallow neural network. So I used the sigmoid, and it worked pretty well. So basically, so if you haven't done a lot of work with neural networks, you can kind of think of it as like the sigmoid, I guess, is kind of like logistic regression. It's 1 over 1 plus e to the x, basically. So either you have either the denominator is really large and the fraction basically turns into like a 0, or it's the e part becomes like a 0 and it's like 1 over 1, so it like kind of approaches 1. So you're bounded by 0 and 1. There's not a lot of neural networks are kind of a black box, and you won't see them, where you have to be able to explain what's going on. They just kind of magically learn some sort of useful input, and so I can explain the math, but that might not really explain like how or why it's working. It just does, and people can't really explain why. Yep. All right, so tips for tuning neural networks. So it was really important to normalize the inputs. I'd heard that would be useful, but I kind of ignored that advice, and then I found out that it makes a really big difference. Probably the most important thing ever is to normalize your inputs. The pixel values for my images from OpenCV are between 0 and 255. So I divided all my inputs by 255, and I got like a 40% accuracy improvement, which is like unheard of by doing that. Deeper is not always better. Deep learning is really popular, overhyped right now, in my opinion, and it did not work as expected for this project. So I just used a shallow neural network, and it worked really well. I might have calculated this wrong. I thought it was 2 or 3, but I have like 200 plus thousand pixels per image. I think the other people might have sometimes some other examples I've seen will use black and white. So they'll have a third of these pixels. You basically, the way that OpenCV, I think most machine vision problems or packages treat images is that they actually have 3 dimensions. You've got height, you have width, and then you have 3 dimensions, one for red, green, and blue. And so if you can compress those color dimension into black and white, you can save a lot of data, or reduce the dimensionality considerably. But my model learned a lot better with color images than with black and white. Anyways, because you have so many pixels, and because I'm not applying a kind of compression algorithm like singular value decomposition or principal components analysis, you just need lots of data. So I collected about 10 gigabytes worth of data. I think NumPy compresses my data, because when I made this as a text file for H2O, it just got huge. But with NumPy, it was like 10 gigabytes of continuous video data. And I have so many pixels that I've never really seen this with any other machine learning project I've done. Adding more data, generally, there's definitely diminishing returns as you get more data. But here, I'm sure there are diminishing returns, but I'm just kind of I'm still very far from that point in the curve. And I actually get a pretty large accuracy improvement when I just add another gig of data. And I think that's probably because of how many pixels I have in each of my frames. To your point, I used the sigmoid activation function. I think it probably worked well because I was using a shallow neural network. But I think it's for some of these research institutions. It's like Berkeley, for example. I think will use neural networks that are like 40 layers deep, which is like unheard of. And when you have that many layers, sigmoid kind of breaks down, and you want to go with the ReLU. But and then I use color instead of black and white. Okay, so Tensor Board. If you use TensorFlow and you want to visualize your neural networks, Tensor Board is the way to go. You can use it for visualizing your accuracy. And if you work with convoluted neural networks, you can see what the weights look like. So I go back to here. If your convoluted neural network is performing optimally, you'll see these shapes that make sense, and you can use Tensor Board to do that. Tensor Board is pretty cool, but it's a little bit clunky. So I won't really cover why it's clunky, but it looks cool, and I'll show you that in action. So basically, TensorFlow writes all of your data to a directory that you specify, and then you can it'll kind of color coordinate all of your different model runs. I have my training and validation or test accuracies printed on the same graph, which you shouldn't really do, but this is, you'll notice that I did a lot of, I trained I've actually did like hundreds of runs, but I've only got like 15 or so shown here. The convoluted neural networks, which are here, which took a super long time to train, I kind of stopped at a certain point because it was just taking like days to run, and the much smaller neural networks learned a lot faster, so I trained them for a lot more epochs. But you can you can use Tensor Board, I think, to get real-time updates from your models when they're training. So that's Tensor Board. Let's see. Okay. So when you're doing your machine learning, it takes a really long time to train your models, at least 4 hours if you're doing convoluted neural networks. And you just don't have time for that, really. So on my Mac, at least it would take 4 or 5 hours for a standard neural network or standard convoluted neural network. But a GPU is really great at speeding that up. And if you can have, I only have one laptop, so even if it ran it fast enough on my laptop, I only have one of these. I can only train one at a time. But if you use something like AWS or some sort of cloud provider like Google Compute Cloud or something maybe, or Azure, you can use GPUs and you can train a bunch of these models in parallel, and it saves you a lot of time and it saves you a lot of money. I was using the first generation of GPUs on AWS. I think it was really cool. I think Amazon released the P2 series, which is like the fancy, expensive version of GPUs. It's like a few days ago, and I haven't tried that yet. I do want to try that. But even on the really old, kind of crappy GPUs, I got a 10x speed up improvement, which is really great. So once you use a GPU, you kind of just don't have the patience for anything else. So once you go GPU, you never go back. Question?
Ballpark, how much you spent on AWS?
So I have used AWS for like big data projects before, and I've spent like, I don't know, $40, and Betty gets a little upset with me. But like I was expecting to spend about, a lot more than that this time. But I got really lucky, and I only spent like 20, I think, or not 20, maybe even like $7. I think $7 is the amount I spent. I would like to use spot instances. If you've used AWS, you might have heard of spot instances, and you can like kind of, rent out servers for like a tenth of the cost that they normally are. I should have used that to get my costs even lower. I would definitely use that for the P2 instances, which are like $10 an hour. But the lower generation or the earlier generation GPU that I was using was like 70 cents an hour. So I ran it for maybe 10 hours, and it was, or give or take, and it was not that bad. Let's see.
Did you train your own neural network, or did you use transfer learning?
Transfer? Oh, I trained my own. Yep. So the point that JetNeat had is there's this really interesting practice that I've never actually done myself, but basically because it takes so long to train these neural networks, you can basically take like the second half or the middle portion of a neural network that somebody else has trained for a completely different problem, because they're learning the basic shapes and contours and objects and stuff like that. You can reuse a lot of those shape primitives to train other things, and it'll save you a lot of time. I didn't do that. I think I would like to do that at some point, just to see how it works. But I just trained my own completely from scratch, and that took a while. So GPUs are really common now if you're doing machine vision. This is the ImageNet. There's basically all these like challenges with publicly available data sets where you have like, I don't know, millions of images, and there's like 1,000 different kinds of things that could be contained in an image. And each image is given a particular label. Like there's a dog in this image, there's a can of some toothpaste in this other one, and a car in this other one. And you basically have to, these different researchers will try to predict, train algorithms that can predict all of these different things. And this is part of the ImageNet challenge. And you can see that the GPU usage has just gone way up over the years. And also the error rate has gone way down. And I think this error rate is what really has made deep learning very popular and kind of buzzword-worthy recently. But the point I wanted to illustrate here is that GPUs are, if you're doing machine vision, machine learning, neural network problems, use a GPU. So just kind of further hammer the point, NVIDIA is the market leader in GPUs, selling GPUs. They've got a 70% market share, I think. I think their market share is going down a little bit recently, but still pretty strong. GPU usage is way up, and just in this past year, I had no idea it went up this much. It basically went up like 200, or the price is 3 times what it was a year ago. It's crazy. If you bought NVIDIA, you would be rich. And so is it a coincidence that GPU usage has skyrocketed and so has NVIDIA stock price? I don't know, but it's an interesting question. So here's their stock over just 1 year period. I didn't know that. I have heard they had some sort of partnership with Tesla, maybe, or is it? They did it on their own. Okay. Oh, well, that's cool. Yeah, so the GPU usage is definitely on the rise. All right, so machine learning takeaways. So I think what I learned, I had really high hopes for deep learning, and I was kind of disappointed, and I kind of think it's a little bit overhyped. Machine learning trends kind of go through this like bubbly phase. I think support vector machines were really popular for a while, like 10 years ago, but then they had their own kind of limitations. I was really, in particular, disappointed with convoluted neural networks, and my really simple network outperformed the supposedly brilliant convoluted neural networks. That was surprising. I wanted to try out 3D convolution. Basically, what that means is, so right now I just feed one individual frame to my my model. But what 3D convolution is actually a series of frames. So you could have like, if you've ever played Mario Kart, for example, or some kind of racing video game, and if you've played it a lot, you'll notice that you shouldn't react to what's happening right now. You want to like look ahead a few steps and be able to anticipate moves. And that's kind of what I was hoping to get with 3D convolution. By looking back 50 frames, I could kind of see where I am right now and what's ahead of me and be able to drive accordingly. But I just kind of ran out of memory, or didn't have enough memory to do that because I had, yeah, so that was a problem. And GPUs actually on AWS, like training this would take forever on my laptop, which has like 16 gigs of RAM, but it's still not a lot. On the AWS GPUs, I have like 8 gigs of RAM, which is nothing. So maybe I could probably intelligently, reduce the amount of compress my images a little bit. But this is still a problem that I need to tackle because I think it is promising. I just haven't really gotten it to work as I would like yet. I tried using scikit-learn, which is, question?
Is it crazy to have a reduced, compressed black and white, just a few pixels that you're using for 3D and have the big current full color and somehow combine those into a single model, or is that?
You could do that, I think.
Okay.
I haven't. It would be a little bit tricky with TensorFlow, but if you use something like, I didn't use scikit-learn, or I'll talk about that in a second. But if you use like a different kind of machine learning library, you can pass however many columns or features you want, and so you could do something like that. Actually, interestingly, convoluted neural networks have a way of compressing. It's called pooling, and you can actually compress parts of the image and not compress other parts. Or I guess you have to compress all of it uniformly, but yeah, what you could do, I'm sure it's what you've described is possible. You can pass however many features you want. You have to be able to cleanly represent that as a matrix. So that can be a little bit challenging, but yeah, but I'm sure it's possible. Let's see. So I tried using scikit-learn. Scikit-learn is, if you're just doing a standard kind of machine learning data science project, that's what you want to go with. And I wanted to try GBM's gradient boosting. Generally does really well. If you compete in Kaggle, it's like almost everybody uses a GBM or a random forest model. It usually beats neural networks hands down. And I was curious how it would do on a machine vision task, but I kept getting sigterm errors. My scikit-learn models just took forever to train, and I never actually got one to complete, so I have no idea how well a GBM would do. But I'm curious. I tried doing this on H2O. H2O is an open source machine learning library. And that had issues as well. H2O works with Apache Spark, and so you can kind of train a model in a distributed fashion. And I do want to try that soon. I just haven't gotten around to it yet. And I'm curious how GBM would do versus my neural network, my single layer neural network. But I haven't been able to answer that yet. All right, car hardware tips. This is kind of a little out of order, but so I have a really small car. That means I have a lot less space. If you want to cram, if you're okay, kind of going with the, having stuff on top, then it's not such an issue. But I'm really constrained for space with this tiny car. A tiny car means you can put fewer things in it, and then the motors are only so strong, so you can't really go very fast. I can't even go on this carpet probably. So that's something to keep in mind. On the other hand, some of these cars can be like $400 if you get one that's like twice this size, and I kind of question. I haven't even heard of that, but that sounds pretty interesting. So like the strength of the motor is really important, at least. Maybe even this, probably the size of the car. The space inside of the car is also really important. Yeah, so get a bigger car if you can. In hindsight, I should have done that. The battery is the heaviest piece, and like the gentleman back there pointed out, why didn't I just use the AA batteries? I think I would have done that if I'd had more time. But if you don't use the AA batteries to charge your Pi, go with the lighter battery versus the charge capacity. Another thing I learned is that, so Google's car has, the actual real self-driving cars have their cameras mounted really high up. You've got a really good vantage point, and you can see the curves, not only the curve that's approaching you, but you can see where your car is right now on the curve. And I went for aesthetics over, function, unfortunately. And my car has some kind of glaring blind spots in the very beginning. So if I'm close to an edge, my car might not realize that, and it can overcorrect sometimes. But I think, if I designed this a little bit better, maybe I would have had the car, better kind of aerial view. So that's something to keep in mind. Let's see. All right, so I still have a lot of work that I want to do on this project. I definitely want to improve the accuracy of the neural network. I want to try gradient boosting. I want to try 3D convolution on Spark for the convoluted neural network. I want to be able to detect stop signs and stoplights and incorporate that as part of the car and also track its distance. I have occasionally these really frustrating video streaming latency problems. So the model might be really accurate, but if I'm getting video frames from 5 seconds ago, who cares how the accuracy is if it's, who knows where on the track. You definitely would not want to have a real car, sit in a live car that has that kind of latency. And it's really sporadic. Sometimes it's not problematic. Other times, who knows what's going on with the Pi. But I have to fix that. Which kind of pops up every now and then. I really want to try the P2 GPUs. I've heard they're on AWS. I've heard they're 4 times as fast as the first generation, and that seems pretty cool. And then lastly, I need to document my stuff a lot better. I have a lot of friends that are like, oh, that sounds like a cool project. I want to, show me how to wire these things. And I'm like, I don't know. I forgot all of it. I have to go back and kind of read through all my notes that are scattered everywhere and clean that up. So you can view, I have all my code on GitHub. It might be kind of hard to understand right now, but I hope to change that soon. And that's it. I started my project in March this year. I'm really dorky and data sciencey, and I track how much time I spend on each of my projects each day. And I know exactly, it's 226 hours or something like that. I've spent a lot of time. It's a big time investment. I'm still making major improvements to it. I'm really, if you play around with neural networks, in particular convoluted neural networks, and you think you might know how to make my convoluted neural networks work better, come talk to me. I'm really curious. But also you can follow my code updates on GitHub. And that's it. Thank you. All right.
So you didn't use any software like fritzing or something to design the circuits? You just plug stuff in and hope for the best?
Yeah, pretty much. I did a lot of Googling. I think I might have broke my Pi that way, maybe.
There is some software that can help you design the circuits, and also in the long run it can actually make print circuit boards so that you can just drop the chips in and solder to them and have a more integrated thing in the long run. If
Yeah.
that's where. But the idea of using something like fritzing gives you a way to document the wiring.
Cool.
That's the most important part about that.
Cool. Yeah, that is something. Yeah, I'll look into that. That's occasionally I'll accidentally unplug a wire, and then I'll have to spend 2 hours figuring out which GPIO pin and whatever I'm supposed to plug it back into. So that's a really good idea. How do you spell that?
Fritzing, Fritzing. I'm just fritzing around.
Cool. Yeah, question over there.
So how do you make the training data set then? So you're driving it off the track and it's driving on the track? How do you
Yeah, good question. So that's actually a really complicated part that I kind of glossed over. But so this the answer to the last part of your question first. You never really want to intentionally drive it off the track because then it'll learn to do that. But what does really help is to get close to start it almost coming off the track so that it learns to correct itself. And I had to do a lot of training examples on that because with the latency and everything like that, it has to be able to correct itself quite a bit when I would deploy it. But yeah, so that's actually one of probably the most complex pieces of my project is how did I actually collect the data? So I had just 3 kind of commands: forward, left, right. I did that from my keyboard on my laptop. I set up a Tornado Python web server on my Raspberry Pi. It's really lightweight. It's very fast. It's asynchronous, and it would basically listen for these commands, left, forward, or right, and then pass those on to the motor, save those commands to a text file, and then simultaneously save the streaming video to an MOV file. And then basically I'd have to, after each training session, each time I was driving on the track, I would have to end all those programs, then SEP my API data from my Raspberry Pi to my laptop, put it in the same folder, and then kind of archive that and redo that repeatedly. So it's challenging because like I had to use these kind of arcane Linux video streaming tools, and so I couldn't have all this kind of running in the same place. I couldn't have it all running in the Pi, and that's, if you look at my code, there's just a lot of like glue code here that I want to clean up. But basically, I drove it myself a lot, and yeah, I did have to do a lot of like sessions where I'm like making it recover from a really sharp turn. Yep.
So how are you tying this image on the screen was the time at which
Mhm.
right?
Yeah, so that's another, that was another kind of thing I had to struggle with. So basically, every time I record, basically the way OpenCV works is, you know what? Let me show you my code. Maybe I'll skim over parts of this because my code can be kind of hard to follow. But basically, every time I record a new frame, I have like a while loop that just iterates through incoming frames. Where is it? Save. Okay, so basically the way OpenCV works is, so I have the streaming video data coming from my Pi at this IP address, basically, and as frames are coming in, while frames are coming in, read the frames, and basically save each frame and a timestamp. I think this is the code that does it. Save each frame and with a timestamp. So I've basically got a file of, let's say I had a really short video session. I had like 100 frames in this one MOV file. I would have 100 timestamps in another file. And then my API, whenever I call my API, I know I only keep track of the deltas. So if I hit up, because I'm not really ever stopping the car, I assume that like I'm going to keep on going, or I'm going to keep going forward until I get my next delta, which is left or right. And then basically I match up the timestamps from the video with timestamps from the commands to know how to assign which commands to which video frame, basically. Yeah, that was a pretty complicated part.
Will you be throwing away any image in which the car just posted, basically?
No, so that's something I might have I maybe should have changed. Like basically, if there's my car does kind of overcorrect sometimes, and that's probably because I never actually tell the car is actually coasting sometimes, but I tell, when I pass in the data to the model, I never actually tell it that it's coasting. I say that this command was always on this entire time. So that's, in hindsight, that might be, I do have times when the car will overcorrect itself, and maybe that's why it's doing that, because it should coast more than I'm telling it it's coasting. Yeah. All right, there's a question over here, I think.
I'm just thinking, I have a, have you played with the NVIDIA Jetson TX1?
I haven't, no. Is that the latest GPU?
So, yeah, do you know if TensorFlow could be installed on that? Anybody know that?
I'm not sure.
The NVIDIA kit, anybody play with the NVIDIA?
Yeah, I really, I know somebody I work with spent like $3,000 on some really fancy GPU, and I would love to do that, but so I wish I knew the answer to your question.
Yeah, I'm thinking about
Getting your own?
Are you doing this with your students? I'm doing something.
Yeah.
I want to do something similar with my students. I was thinking about using the Go by Go that has the Raspberry Pi built on it with the NVIDIA.
Cool. Oh, it's like a pre-built kit, right? So all you have to do is the software. Yeah.
To do anything.
Yeah, yeah. If you just want to do the machine learning part of it or the software part of it, yeah, I heard there are these kits. So this, I think the software side and the machine learning took the most, probably 2/3 of my time. But I spent a good 60, 70 hours doing the hardware. And if you want to skip that part, you can buy these pre-built kits. They don't look as sexy as Ferrari does, but yeah, they have a camera installed, and you can just play around with that. Yep.
Do you have videos of GitHub?
So I made the mistake of putting all my a lot of my videos on GitHub, at least my training session videos, and then GitHub's oh, that's way too much data. Hold on a second. So I have 2 repos. One is with underscores, and that has video data, I think. And then I have this one that doesn't, has just dashes instead of underscores, and that doesn't have video data. So yeah, I do have some, but you have to kind of look around for it. So it's not. When I get this, so like when I've completely finished the project, I'll probably have some animated like GIF video of the car driving. If you're curious about like a training data set, I do have. I put a giant file dump in S3, and yeah, that might work. I have the sets. I have the target variables and the the video frames. So it's like a 10 gig data set, but it might not be. I'm not sure how generalizable it would be. If you do like transfer learning, like Javneet was mentioning earlier, it might be useful, but I'm not sure. Yeah. Question again?
And
Back.
the input for the ultrasound is just ultrasound unit A, yes, no?
So ultrasound. So I actually didn't incorporate that into the machine learning part, but I have like a kind of a rules engine that sits on top of the model that says that kind of overrides any kind of command that the model might give, that the neural network might give. So basically, if anything is this the ultrasound piece. Let me show you the code for that actually.
Like your first law of robotics.
Yeah, pretty much. Yeah. So here's my range sensor code. I'm basically sending out pings every I don't know, really frequently, and then whenever I get a call back, or whenever I get the sound bouncing back, I calculate the time that it took for it to travel, and that's how far away something is. And I'm just running this process continuously in a loop, and that basically if something is I think like 25 centimeters away, I stop because I assume it's some sort of big obstacle, and that's how that works. And that'll override any command I get from the self-driving car neural network, pretty much. Yep.
Where did you get your training data for the stop signs? Is that a separate piece, or is that all just in the same training data you took driving around?
Separate piece. So I actually just got my iPhone and just like click, 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 click. Yeah.
Maybe 100 pictures or so?
Yeah, I think the OpenCV module has. I mean, it's a really intelligent module, hard to use, but does a lot of things. Like one of the things you can do is pass in just a single image, and it will actually scale and rotate and shrink and enlarge the image. So I could have probably just passed in a single image of a stop sign, and it would have handled it. But I wasn't. This is my first time using that part of OpenCV, and I wasn't sure, so I just gave it I think 300 individual stop sign images. Yep. No, So the funny thing is, there was somebody else presenting in the slot like 2 days ago. And then a friend of mine was like, "Oh, there's this opening now. You're working on this car? Do you want to present?" And I hadn't ever made this presentation, so I rushed at the last second to make this presentation, and I haven't put it on GitHub yet, but I will probably after today. Yeah. Any other questions? Yes.
So, production cars out there like Teslas, they have multiple cameras.
Mm-hmm.
And that would imagine that makes it stronger against certain blind spots that you improve to. If you were to add another camera, we would have to do a lot of retraining.
Definitely, yeah. So that's a good question. I'm trying to think how I would integrate that. Yeah, I guess I could. So if I use two cameras, would I put those into the same model, or I'd have to think about that. I probably would have to do a lot of retraining though, but that is really interesting.
So you're thinking just for a moment that you'd have two cameras, each with their own models.
Potentially.
And then some meta model that puts these two things together to wait out the answers from both cameras or something?
Yeah. I think there's lots of different interesting ways you could do that. That's one option. I think you could do like an ensembling kind of thing, which is like, take the average of the two, or you could do some kind of rules-based thing, which is like, favor left turns for this left-facing camera and right turns for this right-facing camera. There's lots of ways to do it. That's one way.
Along the same lines, you mentioned you wish you had put the camera up a little higher.
Mm-hmm.
Have you tried just simply raising it and running your same model, or does that break it down?
That's a great question. I haven't tried that. I do know that for a lot of machine vision problems, people will it's kind of funny how these work. Because I'm taking each pixel as an input, if I shift it just a little bit, like one pixel even, the accuracy will. I haven't actually tested that, but I've seen with other people's models, you can kind of break the accuracy down. So what people will do to kind of get away from that is they won't actually move the camera. You could move the camera, but to kind of get around that, they will actually just literally shift the pixels down, basically recreate a bunch of different images by just moving the frame around a lot. And if I had done a convoluted neural network, I did, but if I had a good convoluted neural network, which kind of is can pick up on shapes anywhere in the image, like regardless of where it is. I probably could have done that, but because of I'm just taking in the pixel values exactly where they are for the single layer neural network, I think it would break down if I moved the camera. Yeah. All right. Any more questions? All right. Well, thank you guys. You were a great audience.